So this is a fun lecture to give, actually, because the theory I'm going to tell you about today has its genesis in this very class, in CS 364A. So the story is 5 years ago, I was in the same sort of segment of the class, teaching a bunch of Price-of-Anarchy analyses. And really just for pedagogical reasons, I was trying to figure out sort of, the optimal way to present all of these proofs to make it as transparent as possible. And as I was doing that, it became clear that there really was, for many of the most well-known Price-of-Anarchy bounds, there was a generic recipe for deriving them. And in fact, that generic recipe can even be precisely formulated as a definition, which is a definition you'll see today. And then what was cool is this definition actually has consequences, implications, and we'll use it today to prove Price-of-Anarchy bounds on coarse correlated equilibria. So those are the biggest set of equilibria that we talked about on Monday, so the hardest worst case upper bounds to prove, and those are the ones we'll be deriving from this definition that came out of the class about 5 years ago. Okay? All right, so before I give you this, so I'll give you this definition, about halfway through class or so. The intent of the definition, again, is to unify a number of Price-of-Anarchy analyses. So before I do that, I want to give you one more important example. So it's an application domain that's already interesting in its own right, but for today it will also serve as another key special case of the general definition. And so, before doing the second Price-of-Anarchy analysis, let me just tell you what are the similarities you should be looking for compared to the one we saw last week, which in the one last week was the 2.5 for the Price-of-Anarchy in atomic selfish routing games with affine cost functions. So it's not important you remember, the calculations, the details from last week's proof, but let me just sort of remind you what the high-level structure of the proof last Wednesday was. So we started, we had an arbitrary selfish routing game, affine cost functions. We started from an arbitrary equilibrium and arbitrary optimal solution. And the very first thing we did is we said, how are we going to ever use the hypothesis that we're working with a Nash equilibrium? And we said, well, Nash equilibrium means deviations only make you worse. So that seems like a good idea. We can generate upper bounds on individual player costs by considering hypothetical deviations. So which hypothetical deviation should we use? Well, sort of the obvious thing to try was the optimal solution. You say, player I, how come you're not doing what you're supposed to be doing in the optimal solution? And that gave us an inequality. So step one was invoke the pure Nash equilibrium hypothesis to derive inequalities of the following form. I'll write it in the notation of cost minimization games that I introduced on Monday. So for a given player I, so here S is the equilibrium, if it deviates, then it only gets worse. And in particular, if S star is the optimal solution, if I deviates unilaterally to what we wish we were doing in the optimal solution, it would only get worse. Okay? And one important point, which I'll mention several times today, is it turns out if you look back at that proof last week, this was the only time we ever used the hypothesis that S was a Nash equilibrium. In effect, after we generated these K inequalities, one per player, we threw it out and never used it again. Okay? That's going to be an important property of that proof. So that was the first thing we did. So second step, there's going to be 4 total. Second step, we just summed these inequalities over all of the players. Okay? And what was really cool about that is we had an upper bound on the individual equilibrium player cost, then we sum over the players, the left-hand side was exactly the equilibrium cost. And in a Price-of-Anarchy analysis, that's exactly what you're trying to upper bound. So the left-hand side after summing was exactly what we wanted it to be. Now the right-hand side was weird. Okay? So we did the sum, and we got this sort of like entangled version of the optimal and equilibrium flows. So in the notation last week, what we observed was we had like a term with the product of F star E and FE. And we had no semantics for that. We just didn't care about it. So step 3, which was kind of the hardest one, was relating the entangled term that we didn't care about to the only quantities that we actually do care about, the equilibrium and optimal costs. So in step 3, we related the entangled term, which was the right-hand side after summing, to the 2 quantities we cared about, the equilibrium cost and the optimal cost. Precisely what we proved is that this entangled quantity is bounded above by 5/3 times the optimal solution plus 1/3 times the equilibrium cost. Okay, that was the precise statement. And then, once we'd done that, we just solved for the Price-of-Anarchy. Okay, so we had equilibrium cost both on the left and the right. We had a 1/3 times it on the right. We subtracted that. We multiplied through by 3/2, and that's what gave us that the equilibrium cost was almost 2.5 times the optimal cost. Okay? So again, not important you remember the details, but this is the high-level structure. I'm going to show you in a different application domain how we can apply exactly the same structure to get another tight Price-of-Anarchy bound. And then we'll zoom out and ask what's the sort of generalization of these arguments, and then we'll turn to applications of that generalization to robust Price-of-Anarchy bounds. So that's the plan. So here's the next application domain. So this is a type of location game, okay, where players are trying to figure out how to position themselves in a network. So the one I want to talk about today, there's a set F of possible locations where players can locate themselves. You can think of these as like, it could be anything from, where you're deploying a, web server cache to, where you want to build the next artisan chocolate store, as you like. There's potential customers, consumers, whatever. It's called the markets. And in each market, there's some value that they have for receiving whatever service all of these players are trying to sell. Okay? And these values are just known. It's not like in mechanism design, everybody knows what the VJs are. Okay? So you know how much money you're going to make from somebody if you can sell them artisanal chocolates. Now, there's also a cost. So for every location L and market J, there's some cost of providing the service or the product to J from L. So in the simplest case, this could just be the distance, but in general, it's just some kind of cost. It could, for example, relate to how well your technology fits theirs. Okay. So the players, each player is just responsible for picking one location. Okay, so one element from the set F. So I'm going to go ahead and just say that each player I has some restricted set of permissible locations, F sub I. If you want, just think of the FIs as being F. Think of that any player can locate anywhere if they want. Okay? But more generally, you can have a permissible locations, F sub I. All right, so in defining a game, what do I need to tell you? I need to tell you the players. I've told you the players. I need to tell you their strategies. I've told you their strategies. So now I have to tell you their payoffs. Okay? So let me do that using an example, and then I'll be clear what the payoffs are in general. Okay? So we have the possible locations over here and the possible markets here. Let's say we have two markets, each with value 3. Let's say there's 3 possible locations. Okay. And let's say there's just 2 players. So player 1 can either go on the top or the middle. Those are its 2 strategies. And player 2 can go in the middle or the bottom. That's the 2 strategies. Okay? So there's only 4 possible outcomes of the game. Okay? 2 strategies for the 2 players. So let me tell you in this example how the payoffs are going to work. Basically what's going to happen is, once these players locate, they're going to engage in price competition to try to sell to these markets. I have to tell you the C's too, I now realize. Okay? So let's say from the top to the top or the bottom to the bottom, it costs 1. So these are the CLJs. And from the middle, it costs 2 to either market. And in fact, let's say it's infeasible to serve the bottom market from the top location or vice versa. Okay. All right, so let me just talk through this. So let me just talk through 2 possible outcomes to tell you how it's going to work. So suppose player number 1 chooses the top location. Player number 2 chooses the bottom location. Okay. So it's symmetric. I'll just talk through player 1's situation. So player 1, if it locates at top, it's unable to serve the second market. That's infeasible. But it can serve the top market at a cost of 1. Okay? And moreover, it has no competition in the top market. Given that the player number 2 has located on the bottom, Number one is the only firm that can actually sell to that market. Okay? So it's just going to price at the highest price it can get away with. Now, the most the market would be willing to pay is 3. So the assumption is going to be that given that there's no competition, firm 1 sets a price of 3, extracts all of the value from the first market. It costs 1 to serve it, so its payoff will be 3, the price that it charges, minus 1, the cost that it pays for a payoff of 2. Same thing down here, exact same reasoning. So suppose instead that player number 1, so that's also going to be a Nash equilibrium in the sense that a unilateral deviation from that could only make your payoff worse. So to see why, so imagine that the top player relocated to the middle. Okay? So a couple things change now. So if you look at the second market, it used to be that the second player had no competition in the second market. It was the only one capable of supplying it. Okay? That's no longer true. With player 1 here, it could also supply the second market, although it would cost it 2. All right? So the way we're going to think about it is, while the second player would love to continue to charge a price of 3 just like before, now it can't get away with it. If it charged 3, it could be profitably undercut by the first player. Okay, we're going to assume a player can serve any number of markets. Okay, so there's no capacity constraints on the players. So if it charged a price of 3, this guy could charge 2.5 and steal away the consumer base. So price competition, given that these two players are at these locations, well, this guy can now get away with a price of 2, or 2 minus epsilon, something like that. So it'll price just low enough that it becomes, there's no incentive for this guy to enter the market. Okay, so this guy will just take the full second market. The value is 3, but it's only going to get a revenue of 2. And then minus its cost will be a payoff of 1. Okay? Now in the middle node, it's still the case that player 1 has market 1 uncontested. And so it's still going to charge a price of 3. But now it pays a cost of 2. Okay, its production, its transportation cost has gone up. So both of the players' costs have dropped, payoffs have dropped to 1 in this case. Okay. So let me write down the general payoffs and then I'll see if it makes sense. So in general, so I'm going to continue to use this sort of S vector notation. This is just a choice of location for each player. And always in this situation, the payoffs we're just going to handle the different markets separately. So the payoff of a player is its payoff from all of the markets. So what's the payoff from a market? Well, basically, to get any payoff at all from a market, first of all, you better be located closer to that market than anybody else. Okay? Because that means you're the unique person who can set a price low enough to get the consumers in that market. Second of all, you better be close enough that you can cover your cost, okay, with their value. Okay? So it's going to be 0. So, okay, let's say I picks location L. So if the cost of serving J from L is more than Vj, then forget it. There's no way to have a profitable transaction. So 0 if CLJ is at least Fj, or if there's some other picked location which is even closer to J. Okay, then they're going to be able to just kick you out with price competition. Okay, so or L not closest chosen location to J. On the other hand, if you are the closest, then you're the one in the position to actually extract the value from that market, and you're going to charge the highest price you can get away with. The highest price you can get away with, well, that's governed by who's second closest. So remember, that's what we had here. So the price that this person could charge at this market was bounded by 2, because that was the next closest location, or the minimum of that and the maximum this person is willing to pay, okay, the value. Okay. So this is going to be, I'll say DJ2. So this is the price you're going to charge. This is the cost that you still have to pay. And the definition of this is just the minimum. Okay, you can't charge more than they're willing to pay. And then you also can't charge higher than the point at which the next closest person could undercut you. Okay. So in effect, what we're saying is that as a player, the revenue that you can capture, your payoff, that is going to be your sort of competitive advantage with respect to a given market. Okay, so a different way of thinking about it is if your cost is better because your technology is better, then your payoff is going to be the extent to which your technology is better than everyone else's, and your serving cost is less. Okay, so we think of players as picking these locations, then people just charge the highest prices they can get away with, and this winds up being their payoffs. If you want, you can sort of derive these payoffs from first principles. You can set this up as a three-stage game. You can study what are called sub-game perfect Nash equilibria, which are appropriate for games with multiple stages. We're not going to talk about them in class, but it is covered in the AGT book if you're interested. Okay. One other thing I'll say is, we've sort of flipped maximizing versus minimizing compared to routing. Routing, we wanted to minimize costs. Here we want to maximize payoffs. Needless to say, that's just a cosmetic difference. Okay. All right, so what do we want? So we're going to study surplus maximization. And in this context, surplus is just the value provided, so the sum of all the VJs of the markets who are served by somebody minus the costs. Okay, so minus the CLJs for everybody who gets served. So let me just write that this way. So I'm going to use the notation capital V to denote the surplus, which is a function of the chosen locations. And again, we're just going to add it up market by market. And I'll write it this way, where DJ is the same thing as DJ2, except it's about the closest location, not the second closest location. Okay. So this is the minimum of VJ. So, if the closest person is further than VJ away from you, you don't get served at all. So this is just going to be 0. Or the closest location to J. So for example, up here, in the first outcome we looked at, with one player on top, one player at the bottom, both markets are served, so that's a 6 minus a cost of 2, so that would be surplus 4. If the player moves from top to middle, again, both markets are served, but now one of the transportation costs has gone up to 2, so the surplus would drop from 4 to 3. Okay? So that's the description of the model. All right? So when we talk about the price of anarchy in games like this, we're just asking what fraction of the maximum possible surplus are Nash equilibria guaranteed to achieve. Okay? So that's what the theorem is going to be about. So any questions about the model, the description of the model? Yeah.
When you say second closest location, it's location that are being picked by somebody.
Exactly. Yeah. So I didn't write it down, but this is closest location actually chosen by a player, and similarly here, second closest location actually chosen by a player, and same thing here. Okay. So if you want, the unchosen ones, just think conceptually of deleting them, and then do these computations. Yeah. And I also, so this of course is a function of S, right? So this depends on which locations were chosen. I didn't write that notation, but keep in mind that S determines what these numbers are. Yep. It is allowed. And what was the second question? Does it give what?
Oh, so if it's not allowed?
No, it is allowed.
Oh, it is?
Yeah.
So then does that give a surplus of 2 or 0?
Just think about what would happen in real life. So suppose there were literally 2 stores selling the same product at the same place, right, with nothing to differentiate them. So the price competition would just drive the price down to whatever the cost of service was.
At which point none of them has not sold all.
Yeah, so you wouldn't expect this in Nash equilibrium, but it is allowed. So, basically both markets are going to be served at a price of 2. So the surplus will be fine. So remember, surplus just says how efficiently, so first of all, how many people are actually being served, and secondly, how cheaply is it being done? Okay, and that's the surplus. Then there's this other question of how is that surplus split between the consumers and the sellers, right? So how much of it is revenue and how much of it is consumer surplus? And so the consumers would love it, right, if people co-locate, because then the prices are going to be low, and the surplus is going to go to them. But we're thinking more of sort of the firms as being the strategic players, and so they're actually in general going to want to try to segment the market in equilibrium. Yeah. Hmm?
Why is it that
Yeah, so again, surplus is just about how efficiently the allocation happens. But the payoffs are in terms of revenue. And so, if you look at the global system, arguably what you care about is just you want technology to go to as many people who want it as possible, as cheaply as possible. But then, of course, the firms care about how much of that surplus goes into their pockets. So there's the usual friction between those two. Okay, so here's the theorem I'm going to prove. This is an old theorem of Vetta. So in every location game, every Nash equilibrium, and I'm not going to prove it, but there can be multiple equilibria in these games, but every pure strategy Nash equilibrium captures at least 50% of the surplus. Okay? So obviously in general they might capture more, but this just says in every single game, every single equilibrium, the worst you're ever going to see is 50%. This turns out to be tight. On the next exercise set, it asks you to provide an example showing that 1/2 is the optimal result. So the way I want to structure this argument is I want to first talk about 3 properties that these games have. And in fact, these 3 properties are the only ones required to actually establish this bound at 0.5. Okay? So key properties. So for the first one will seem very intuitive given everything we've said about auctions, which is just that the sum of the players' payoffs, okay, i.e. the revenue, is bounded above by the surplus. Okay? Say it again? Oh, I meant to comment on that. So this is a maximization game. Okay? But I mean, you have to make some choice about which way to define the Price-of-Anarchy for maximization games. So we're defining it in exactly the same way as before. Objective of equilibrium over objective of optimum. So this is exactly what we wrote for cost minimization games. For cost minimization, this was at least 1. For payoff maximization, this is a most 1. Okay? But again, good means close to 1. That's always true. Max or min. Okay? So you will see in the literature some people, prefer to always have these numbers at least 1. So they'll just sort of flip the numerator denominator. Okay? So we're going to prove that this is at least 1/2. That is, again, surplus of equilibrium is at least 50% of the best possible. Okay, so as I was saying, so again, I want to state 3 properties, and then I'll prove them, but they're all quick proofs, and then I'll use those 3 to derive the bound. So the first property, look at the total payoffs of all of the players, so that is their collective net revenue. That's at most the surplus. Okay? And again, we saw this over and over again in auctions. The revenue you extract from people can't be more than the surplus that you generate. So I'm not going to write proof, actually. So this is just because let's compare payoffs with the objective. So the payoff, this is sort of the cost that you incur individually and also society. And then what you, as a seller, take home is either, whichever is smaller, the second closest chosen location to J, or the maximum they're willing to pay. Okay, so this is always going to be at most Vj. So the sum of the pi i's is always at most V. Okay. All right, so that's the real easy one. Can't extract more than the surplus as revenue. So secondly, we have an interesting property of these games, which is there's a nice way to think about just exactly how much revenue one of these sellers does take home in their pocket. So the amount of money that you make in this game is exactly the extra surplus that your location provides to the system. Okay? So your payoff is exactly the extra surplus over what it would be if you weren't there. Okay? If I just deleted your location. So this requires a proof, although it's just really a one-liner. let's just sort of think this through. All right, so the right-hand side here. So imagine you have k minus 1 players and they've picked their locations. Player k shows up with his new location, okay, and we put that into the system. So how does the surplus change? So what's the surplus? Well, it just decouples over the markets. And the surplus of a given market is the difference between its value and the distance to its nearest chosen location. Okay? So for a given j, there's two possibilities. Either this new kth location is its new closest location, or it's not. If it's not the new closest location, there's no change in this market. It's the same as before. If this isn't the new closest location, then the jump in surplus is exactly the extent to which this is closer than the previous one. Okay? So the jump in surplus, when you add a new location, is you sum over the markets, and you just say, well, what was the distance of the old closest location? And what's the distance of the new one? Okay. And if you think about it, what do you take home in your pocket as one of these firms, one of these sellers? Well, again, you sum over the markets, and what you take home is exactly your competitive advantage, the extent to which you are closer to it than the second closest competitor. Okay? So it's just exactly the same as the payoff. So that's property 2. Property 3 is that the welfare function v is what's called submodular. I think many of you have probably encountered submodularity on the homeworks, but I'll certainly remind you what it is here. Oh, one aside is, so this property 2 is a pretty nice property. It shares some of the spirit of VCG. If you recall, the way we define payments in VCG was internalizing externalities. In some sense, the rebate that you get should be exactly the surplus that you added to the system. In fact, this property lets you prove that these location games are potential games in the sense of Monday's lecture, where the surplus provides a potential function. Okay? All right, submodularity. So submodularity is a form of diminishing returns. So what you want to think about is you want to think about a small set of locations, then a bigger set of locations, and then the case you should keep in mind is where we're thinking about a location which is not in either of those. Although actually it doesn't matter, but this is sort of the case that's the most relevant. And we want to say, what is the added value of L to T1, and what is the added value of L to T2? And so diminishing returns just says T2, being that you have more stuff already, the added value should be less to the bigger set T2 than to the smaller set T1. So what this means is that for all locations L and sets of locations T1 and T2, again, if you look at the value added of L to the bigger set, that should be bounded above by the value that L adds to the smaller set. Okay? So this is the definition of submodular. So that's what I mean when I say this. Now, why is it true in location games? Well, it's true basically just if we kind of recall our discussion of surplus, and we recall this equation star. So remember, back in star, we were reasoning about how the surplus changes when we added a new location. So that's very relevant here. We're thinking about adding a new location to a bigger set or a smaller set. And we argued that the jump in surplus is exactly summed over the markets, the extent to which the distance to the closest location has gone down. Okay? And market by market, that's true. So if I just throw sort of extra locations into the system, okay, the distance between the closest one to a market is only going down. Okay, so the value you add can only be dropping as there's more and more other people who might be the previous closest location to the market. Okay? So that is, if you inspect star, which expresses surplus increase as you add one new location, then the bigger the set T that you're adding something to, the smaller the previous D sub j's. Okay? So the closer the previous closest location would be. So that's why the net increase in surplus from adding a new location is only going down as the set that you're adding them to is going up. Okay? So those are the three properties. Okay? So given this, we're going to prove that in these location games, or really in any game that satisfies these three properties, of which location games are one of, in fact, many interesting examples, as long as these three properties hold, Nash equilibria capture half of the surplus. Any questions before we do that? Before we prove the 1/2 bound?
So when you start back there, pick the outside nodes, then you got like is that fit with our model or is that happening more? Because if it said it's like the minimum of B sub j and the second lowest.
Right. So in the example, in the first outcome we talked about where there's one person on top, one person on bottom, D sub j of 2 was plus infinity. There was literally I didn't draw those edges. So basically the other person wasn't even in the market. So it was the minimum of 3 and then plus infinity. So that's why it was a 3. Okay. So here's how we derive Vetta's theorem from properties 1, 2, and 3. And this is the point at which we're going to mimic the 4 steps that we did, proving the 2.5 for selfish routing and the Price-of-Anarchy there. So again, we're going to use the Nash equilibrium hypothesis first, once and only once. We'll never use it again. For each player, we'll ask, how come you're not doing what you're supposed to be doing in the optimal solution? And in this case, it's payoff maximization, so we'll get a lower bound on the equilibrium payoff of each player. Then we'll sum. Then we'll have an entangled term. Then we'll have to apply, this is where the non-trivial work is, so properties 1 through 3 are mostly relevant for disentangling the entangled term, and then we'll solve for the Price-of-Anarchy. Okay, so we're going to do that again right here. So, consider an arbitrary location game. Consider a pure strategy Nash equilibria, S, and an optimal solution, S star. Optimal meaning maximizes surplus. Okay? So step 1, use the Nash equilibrium hypothesis. So what does that mean? That means deviations only make people worse, only decrease the payoff. In particular, if someone tries to unilaterally deviate to their strategy in S star, their payoff only drops. Okay? So in equilibrium, they're doing at least as well as how well they'd do if they switched to its location in the optimal, and everyone else stayed the same. Okay? For all I. All right. And again, it turns out, for the rest of the proof, we'll never again use the assumption that S is a Nash equilibrium. Okay? This is the only time we ever use it. Second step is we sum. And again, the reason we do that is because then the left-hand side is something we care about. Okay, is the equilibrium objective function value, or almost in this case. So if we sum over all I, we get that the sum of players' payoffs is at least this entangled thing we don't care about. Yep. So that's clear, I hope. Now, this left-hand side is also not what our theorem's about. Our theorem's about the surplus of an equilibrium, and this is just the sort of net revenue to the sellers at the equilibrium. But remember, property 1 of these games says that you can't extract more than the surplus. So you can certainly use the sum of sellers' revenues as a lower bound on surplus. And this is what we're trying to prove something about. Okay? We're trying to prove that the surplus of the equilibrium is pretty good. It's at least something else, at least some fraction of optimal. Okay? Where are we? There we are. Okay, so that's step 2. Now step 3 is the work, generally, which is how do we take a quantity we don't care about, it's this weird mixed up version of the equilibrium and the optimal solution, and relate it back to the only 2 things we care about, in this case the surplus of the equilibrium and the optimal solution. So what we're going to prove is the following, and again we want lower bounds on equilibrium surplus. So we're going to take the entangled term and lower bound it by the optimal surplus. Okay, that's a little bit too good to be true, right? Because remember, a chain of inequalities starts with the equilibrium surplus, and it's not going to be the case that every equilibrium is fully efficient. So minus, okay, so it's at least the optimal surplus minus something, and we're going to prove it's minus the equilibrium welfare. Okay, so it's at least the optimal welfare minus the equilibrium welfare. So step 3 is proving this claim. All right, so the first thing we have going for us is that we have a way to take seller payoffs and relate them to surplus in the system. Okay, so we have this kind of VCG-like looking property 2, which says that the payoff enjoyed by one of these sellers is exactly the surplus its location is adding to the system. Okay, so that lets us write, instead of pi's, let's just write v's. So that seems like progress. Okay? So by 2, the left-hand side, so this is just the surplus in the entangled outcome minus the surplus if I wasn't there at all. Okay, so this is by property 2. Now, you look at this and you have a little bit of hope because it's sort of this summation of differences, and it doesn't seem like the terms are changing very much for the different indices. So this sort of has the flavor of a telescoping sum. Okay? Now it's not a telescoping sum. If you look at I and I plus 1, it's not the case that you get a cancellation. But the next and basically final step is to massage this so that it is a telescoping sum, and that's where we use submodularity. Okay? Why might submodularity be useful? Well, what is this? This basically says what is the added value of the location chosen by I in the optimal solution? What is the added value of S star I, given that you already have S minus I? Submodularity says diminishing returns, which says we can lower bound this difference by the added value of adding S star I to any bigger set, any set bigger than S minus I. Okay? That's what submodularity says. And once you have that idea and you stare at this a little bit and you have the goal of making this telescope, you can figure out what's sort of the right set of players to add to S minus I, okay, to get the thing to telescope. Turns out the right set to add is you want to add SI back in. Okay, so I's equilibrium location, plus to get it to telescope, you want to add in the optimal locations of the first I minus 1 players. Okay? So let me write that down. So by 3, meaning submodularity, if we look at this difference, so the added value of S star I given S minus I, that's lower bounded by the added value of S star I in any bigger set. In particular, I'm going to add in the optimal locations of I through I minus 1, and I'm going to look at the equilibrium locations of all K players. So this is a set of K plus I locations. Okay. Minus, again, it's S star I's location I'm thinking about its added value. So it should be absent over here. So this only goes up to I minus 1. And again, I'll have all of S. Okay. So that's by submodularity. And again, really just by construction, I've chosen this maneuver so that the difference of welfare terms telescopes. So now if you look at the right-hand side here and you compare I and I plus 1, you'll notice there is a cancellation. Okay? So this term will cancel with the minus term with I plus 1. Okay? So that means once you plug in this lower bound into the sum telescopes, we're left only with a positive contribution from the very first summand in its first term and a negative contribution from the second term of the last summand. That is, so the biggest of all the sets is just the two k locations, the equilibrium locations S and the optimal locations S star, superimposed. This is what you get from the first summand. And at the very end, do I have it reversed? Let me have it reversed. Minus V of S bar, equilibrium. So you have the minus term from the first summand, that's this, and then you have the plus term from the final summand, that's this. Okay? That's what you get after the smoke clears. Okay? That's what's left. If you think about it, surplus is definitely monotone. You add more locations. The closest locations to places are only getting closer, so the surplus is only going up. So I can lower bound this by just the surplus in the optimal solution minus the surplus in equilibrium. Okay? As claimed. So that was the hard work. So that was the disentanglement step for location games. You can lower bound the entangled term by the difference between the optimal and equilibrium welfares. So step 4 of the template is now, after you've done the disentangling, you just solve for the price of anarchy. And so putting together steps 1 through 3, we have on the left-hand side the equilibrium welfare. We have on the right-hand side the difference between the optimal and the equilibrium welfare. So if you rearrange, you just get that price of anarchy, which again I'm defining as the fraction of the optimal surplus achieved by the equilibrium is at least 1/2. Okay? And that's the proof of Vetta's theorem. Any questions about that? So again, one point of this is just here's another relevant application domain where it turns out it's analytically tractable to understand how close to optimal equilibria are. And especially given that you're looking at both worst case games and worst case equilibria, it's quite pleasing that it can't be arbitrarily far away from optimal. Okay? Even for worst equilibria, it's 50%. And of course, in general, it will be better. So that's point number 1 of these location games, and that's the reason they were originally studied long ago. But the sort of higher order narrative is that they furnish a second very nice example, the first being atomic selfish routing. So a second very nice example of what are called smooth games. Okay? And the definition of a smooth game is meant to articulate exactly what one of these 4-step price of anarchy proofs looks like. Okay? So this is going to be the precise formulation of what this generic recipe for proving price of anarchy bounds is. So I'm going to give you this definition, and we'll observe that these are 2 special cases of the definition, and then we'll move on to applications. So nice properties of smooth games. Okay? So questions before that? Okay. All right. So So I'm going to give you separate definitions for cost minimization games like selfish routing and payoff maximization games like that location game, but they're pretty much, obvious analogs of each other. So let's start with cost minimization games. So there's two parameters, lambda and mu. Okay, these corresponds to the two coefficients in these disentanglement arguments that we've been looking at. So they're going to correspond to 5/3 and 1/3 in the disentanglement argument from last week. They're going to correspond to 1 and 1 in the disentanglement argument I just showed you here. So lambda mu smooth, and for the cost minimization case, we need mu less than 1 if the following property holds. Basically, if you can disentangle. So if the entangled version of an outcome S star and an outcome S, and again, what do I really mean by entangled? I mean a vision starting with the K vector, okay, the strategy profile S. And then think about all the single component changes you could make. Okay, you could go to its ith component and you could change it into some other one S star I. Okay, so starting with the starting point of S, there's K different vectors you can get by changing a single component. These are those K other outcomes. Okay, that in some sense are at Hamming distance 1. And we just look at the cost of the deviator, the person who changed, and sum them up. This is the entangled term that we kept seeing. Again, we don't care about this per se. We just want to relate this to what we do care about. So lambda mu smooth just means you can relate this back to the cost of S star with the coefficient of lambda plus mu times the cost of S. Okay? And here, you might, if you're wondering what this cost operator is, this is just any objective function which is bounded above by the sum of players' payoffs. Okay? So where cost of an outcome is an objective function satisfying this inequality. With selfish routing, this held with equality. Okay? Those were our various expressions of the total travel time. Okay? Oh, I almost forgot the most important thing, which is this should hold for all outcomes S and S star. Okay? We may have in mind, as a particular instantiation of this inequality, we may be thinking or guided by the case when S is in equilibrium and S star is an optimal solution. But that is not what the definition says. The definition says for every pair of outcomes, no matter what they are, you should be able to disentangle. So for example, in a selfish routing network, any two pairs of traffic patterns, arbitrarily crazy traffic patterns, this inequality should hold. Not just under the assumption that one is in equilibrium or the other is an optimal solution. Okay? So that's what it means for a game to be smooth. And then for payoff maximization, there's an analog. So now the entangled terms are in terms of payoffs. Now because you're maximizing, you want a lower bound. And again, because you're maximizing, you're going to subtract off an error term rather than add an error term. And again, this is where it should have the property, like in the location games, where the objective function you care about can be bounded below by the sum of player payoffs. And again, this is for all S and S star. Okay. So that is the definition of a smooth game. Okay? So given any pair of outcomes, S and S star, if you form this entangled version where you take S as a starting point to look at the K ways to massage it in one component toward S star, look at the cost of that massaged outcome, and you sum those up, you can bound those against a linear combination of the two outcome costs S and S star. That's what it means. We've seen two examples. It won't necessarily be obvious to you, but you should go back to your notes and verify this. If you go back to our proof 1 week ago, that the Price-of-Anarchy in atomic selfish routing networks with affine cost functions is 5/2. What we actually proved in step 3 in the disentangling, we actually proved that every such game is smooth with the parameters 5/3 and 1/3. Okay? And the reason that's what we actually proved is that in step 3, while we had in mind that S was an equilibrium and S star was an optimal solution, we never used that fact in the disentanglement argument. That was all just algebra. Remember, we had this sort of y times z plus 1 as opposed to this 5/3 y squared, blah, 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 blah. That was just about numbers. It wasn't about equilibria. Okay? So we proved the disentanglement for all pairs, not just for equilibria. Similarly, in the proof I just gave you, it was only in step 1. We used that S was an equilibrium. And in the disentanglement step, that was just algebra. Submodularity, telescoping sums had nothing to do with equilibria. So we actually verified these conditions in both of those examples. Okay. All right, so that's fine. So this is just all you should be convinced of now is I've given you sort of a common language to talk simultaneously about multiple Price-of-Anarchy proofs. Which is nice, but it's not necessarily clear that it's good for anything. So in the rest of the lecture, I want to explain some of the things that it's good for. Okay, I want to tell you about when you actually wind up verifying these smoothness conditions, automatic and interesting consequences that those games enjoy. So let me begin by connecting things to the main topic of Monday's lecture, which was our hierarchy of equilibria. Pure strategy Nash equilibria, mixed strategy Nash equilibria, correlated equilibria, and coarse correlated equilibria. The theorem I'm about to state is about the biggest set, coarse correlated equilibria. So let me remind you of the definition. Plus mu.
Why is there a minus in the, just doesn't seem intuitive.
In the payoff?
Cosmization is like lambda v minus mu v.
That's right.
And cosmization is lambda cos plus mu cos.
That's right. The reason is just, it's just because of max versus min, right? So, you'd love to be, so like imagine if lambda was 1, which it actually was in the location game example, okay? So imagine lambda was 1 and mu was 0, okay? That would imply something incredible, which is that equilibria are fully optimal. Okay? So in effect, so the mu term lets you say something weaker. It says, okay, well, we're not going to claim that the equilibrium is at most 1 times an optimal solution. We're going to claim that it's at most 1 times the optimal solution plus or minus an appropriate error term. Now, if it's something that you want to be small, then the error term is something you'd add. That would weaken your statement. So that's the reason for the plus mu times cost. If you're trying to lower bound the cost of an equilibrium, and you want to have a weaker statement which is actually true, then you want to subtract something off.
The second thing is the condition on mu less than 1 is the same for a pair of factors.
No, it's not actually, but again, it's not. I wouldn't necessarily worry about. It's just, it's not for interesting reasons. You'll see exactly, the mu less than 1 will become clear in a sec for the cost minimization case. So think of these as despite some minor syntactic differences, think of them as basically just being exactly the same thing for minimization, maximization. Okay, so when you work it out, this is just the appropriate version for the two cases. Okay, so we had this hierarchy of equilibrium concepts. And so maybe just remind you of the motivation. So again, pure strategy Nash equilibria may not exist. Okay, including in games that we care about, like selfish routing with weighted players. Mixed Nash equilibria always exist, but are hard to compute. Okay? So that motivated looking at even more permissive equilibrium concepts. Correlated equilibria were easy. You can find one in polynomial time. There are distributed learning algorithms that drive joint play to that set. Coarse correlated equilibria are even easier. Okay, in a couple lectures, I'll actually show you the very lightweight learning algorithms that drive joint play into this set. Okay, that's one of the topics coming up soon. All right? But so the point is, coarse correlated equilibria, being so big and so permissive, are a pretty plausible, relatively, prediction of what might be happening in a game. Okay, a lot of outcomes are coarse correlated equilibria, so it's just sort of a very It's a relatively weak prediction about what's actually happening. Okay? So what's the definition? So a distribution sigma over the outcomes of a game. Okay, so over the product space, A1 times A2 times AK. If, so as usual, you think about all potential deviators, you think about all potential deviations, SI prime. Here AI is the strategy space for player I. And what you compare is you say, well, suppose I always played as recommended by sigma. So if we envision sort of drawing an outcome at random from sigma, so then I's cost is a random variable, depends on the chosen outcome, but we can look at its expected cost. It just plays according to sigma's draw. And we compare that to how well I would do if instead it deviated unilaterally and unconditionally, okay? Whereas everybody else continued to follow S. So that would be the expected value, where I switches to SI prime. This is deterministic. This is random. Okay, this is being chosen from the distribution sigma. This is a fixed pure strategy deviation. And if that inequality holds for the expected cost of every player, for every deviation by a player, then it's called the coarse correlated equilibrium. Okay? And again, generalizing all of the previous equilibrium concepts that we saw. And again, the point that we concluded with on Monday is that because the Price-of-Anarchy takes the worst case over all equilibria, as you widen the set of equilibria, the good news is that you're more likely to have existence. In fact, you always have it as soon as you're at mixed strategy Nash equilibria. You're more likely to be tractable, and indeed you're already tractable at correlated equilibria, but the Price-of-Anarchy only gets worse because there's only more equilibria you're trying to bound. Okay? So the strongest type of Price-of-Anarchy arguments abounds with respect to this picture would be for the biggest set, for the coarse correlated equilibria. And so what's cool is if a game is smooth, then even though in your mind perhaps you merely thought you were proving a bound on the Price-of-Anarchy of pure Nash equilibria, when we were talking about routing games, we never talked about randomization. We just sort of proved with our bare hands this 2.5. In this location game, we didn't even talk about mixed strategy equilibria. We just talked about pure strategy Nash equilibria. We proved a 0.5. We inadvertently, it turns out, proved that exact same Price-of-Anarchy bound for all of these, okay? By verifying the smoothness condition. So formally, here's what's true. I'll just state the cost minimization version, but the other one's analogous. So in every lambda mu smooth cost minimization game, and again, mu should be less than 1, the Price-of-Anarchy is the most lambda over 1 minus mu. Okay? So just to help you relate to this formula, so in selfish routing, we verified the smoothness condition with lambda equals 5/3 and mu equal 1/3. And so therefore lambda over 1 minus mu is 5 halves. Okay? So the way to think about it is not so much lambda over 1 minus mu per se. The way to think about it is we proved a bound in our mind just for pure equilibria, but because we proved it in a particular way, following this canonical recipe, that exact same number, whatever it is, we get it for all of the sets, all 4 of the sets. Okay? It holds all the way out to coarse correlated equilibria. Okay? So in this sense, it's a type of Price-of-Anarchy bound that extends automatically from pure equilibria all the way out to coarse correlated equilibria. So for payoff maximization, the only thing that changes is mu no longer needs to be at most 1, and it's now going to be a number less than 1, lambda over 1 plus mu. And so again, for the location games that we just discussed, lambda was 1, mu was 1, and that's the 1/2. So again, the point is, we thought we were proving a 1/2 for pure equilibria. We actually got it for all of these equilibria. So any questions about what the theorem is saying? So I'll give you a proof, but frankly, the proof, once you sort of think it might be true, the proof writes itself. So, as you'll see. So again, in particular, this tells us 2 examples with good Price-of-Anarchy bounds, even for coarse correlated equilibria, which again means even, say, for agents who are distributively trying to play this game using very simple learning strategies. It says even though they may never converge to a Nash equilibrium, because they're going to be in this big CCE set, these bounds of 2.5 or 1/2 still apply. And these are not the only 2 examples. They're the only 2 I'm actually going to show you in lecture, but there's many other examples known at this point. Okay. So proof. And again, we can just really just follow our nose here. So what are we trying to argue about? We're trying to say that coarse correlated equilibria are near optimal. Okay? So consider, I'll prove the cost minimization version. So consider an arbitrary lambda mu smooth cost minimization game. Consider an arbitrary coarse correlated equilibria. And what we want is we want an upper bound on the cost of this coarse correlated equilibrium. Now this thing's randomized, so when I say cost, I really mean expected cost. Okay? And expected where we just look at the distribution over outcomes that sigma is doing. Okay? So you think about, remember like the traffic light, right, where sigma picked 50-50 between 2 outcomes. Okay, so they may have different costs, we're just averaging over all the things that sigma might pick. All right, so again, we can just think about, all right, what do we got going for us? What are our hypotheses, right? And we don't have many, because now things have gotten pretty abstract. Kind of all we know is that this is a coarse correlated equilibrium. So we've got this to work with, and we know the game is smooth. So I guess I've erased it, but we have the disentanglement inequality to work with as well. All right? So nothing's entangled yet, so it seems sensible to start here. So that's about individual player incentives. Okay? So this is about joint costs, but really we want to talk about individual player costs. But remember, we're assuming that the joint cost is bounded above by the individual player costs. And again, this held with equality for selfish routing, but in general, as long as it's player costs are an upper bound, we're fine. So this is starting to look sort of like what we want. Okay? But the equilibrium condition doesn't apply to the joint cost, it applies to an individual cost. So we'll just use linearity of expectation to take the sum out here. And now the CCE condition is looking pretty relevant. Right? So this is the expected cost of player I in this coarse correlated equilibrium. By definition, in a coarse correlated equilibrium, if you make any unconditional deviation, you only get worse. Okay? And again, which deviation should you try? Well, again, the optimal solution provides one to try. So we could think about, as a thought experiment, player I just deterministically picking its strategy S star I in the optimal solution. By the CCE condition, its cost would only go up. So I'm really applying this condition once for each player, where S star I is playing the role of S prime I in the definition. So now things are starting to look entangled. Right? So now smoothness is starting to look like maybe it's the appropriate tool. Now, smoothness, I guess I've erased it. Let me put it back up there. So smoothness says this. So smoothness talks about an entangled version, meaning the sum of players' costs and these entangled outcomes. So that's not quite what we have here. Here it's just sort of about a single player and its experience in a particular entangled outcome. But again, lineative expectations lets us focus instead on the expected value of the entangled term that we want. So let's just move the sum back inside the expectation. And now we're in business, right? This is exactly the entangled term that smoothness allows us to relate back to things that we care about, the cost of S and the cost of S star. Now notice, it's very fortunate that we can disentangle any outcomes, any outcome S, not just Nash equilibria, because if you look inside here, what do we know about this outcome S? We know very little, okay? So sigma is some distribution over outcomes, okay? You're doing this with 3% probability, this other outcome with 17% probability, et cetera, et cetera, et cetera. There's no guarantee that these things are Nash equilibria. These could be anything. The only thing we know is an equilibrium condition on average over the outcomes. Okay? We do not know that any individual outcome that we're averaging over is an equilibrium itself. So the fact that we've proved this not just for equilibria, but for all outcomes S, gets used exactly in this part of the proof. S is random, but I don't care what it is. It doesn't matter what it is. I can always relate this back to a linear combination of S and S star. So by smoothness, we get that, the expected value of this convex combination. Okay? Now S star, right, this is just the optimal solution of the game. Right? So this is deterministic. Right? So there's no randomization over S star. The game is fixed, the optimal solution is fixed. So this is just lambda times the optimal cost. Now this is what's random. Okay? This is what's being chosen from sigma. So we can take the mu out times the expected value of this random outcome. Okay? So now, where did we start? We started with the expected cost under this coarse correlated equilibrium sigma. And we've said that that is bounded above by lambda times the optimal cost plus mu, where mu is less than 1, times the same thing we started with, the expected cost at equilibrium. So now we just solve for the price of anarchy. We subtract this from both sides. It gives us a 1 minus mu on the left-hand side, and we divide through. And that gives us that the expected value of the coarse correlated equilibrium is the most lambda over 1 minus mu times the cost of the optimal solution. So that is why in smooth games, you automatically get bounds for coarse correlated equilibrium. Questions?
What is cost of S if not the sum of the cost of its correctness?
It can be an arbitrary upper bound. So like in the location game, whereas a payoff maximization game, we observed that the sum of the player payoffs was not necessarily equal to the surplus. It could be less. So it's whatever you want it to be. But as long as the inequality holds, then the proof is correct. Other questions? So there's a bunch of other things, properties that smooth games have automatically. I won't have time to tell you about many, but let me mention one other one that's simple, which is to an orthogonal set. It looks like that, which is approximate pure strategy Nash equilibria. So I'll tell you exactly what I mean by that. There's multiple ways to define approximate Nash equilibria. But the upshot is that in smooth games, as you relax the equilibrium condition, the price of anarchy, as you'd expect, degrades. Right? So in particular, if stuff is arbitrarily weird, arbitrarily non-equilibrium, there's nothing you can prove about it. But as you relax the equilibrium condition, the price of anarchy bound degrades gracefully in smooth games. Okay? So precisely, again, I'll just state it for cost minimization, but there's an analog for payoff maximization. So S, and this is now just a deterministic outcome, although you could, of course, have analogs for all the other equilibrium concepts if you prefer. So S is an epsilon approximate pure strategy Nash equilibrium if for all players I and for all deviations, well, maybe there's a deviation that makes you better off, but not by much. Okay, just by the 1 plus epsilon factor. Okay, that's what it means. So do the cost at equilibrium. Maybe it can be strictly bigger than something with a deviation, but only by 1 plus epsilon. Okay. So that's one natural definition of an approximate equilibrium. And following this exact same sort of derivation, in fact, the easier version because there's no randomization in this version, so if a game is lambda mu smooth, and S is an epsilon approximate pure Nash equilibrium, then the cost of this approximate equilibrium divided by the cost of the optimal solution, well, we're not quite going to get our lambda over 1 minus mu bound. That'd be a little bit too good to be true, right? Because we're allowing some violation in equilibria. We expect the price of anarchy to jump up beyond lambda over 1 minus mu. But we just pick up a 1 plus epsilon on the lambda and also a 1 plus epsilon on the mu. And this is meaningful assuming that this denominator is positive. So that's going to be epsilon is at most 1 over mu minus 1. Okay? And again, once it occurs to you the definition might be useful, proofs like this just sort of write themselves. That's what we're going to ask you to do on the problem set that goes out, on the exercise set that goes out today. Okay? So that's it for smooth games. Have a good weekend. See you Monday.